Obermeyer.
Thanks so much for having me. It's particularly nice to be here because normally I can't figure out why anyone invites me to any conferences, and I always have this suspicion that it's so that I can provide like medical assistance if someone needs it. But the Zoom format means that that can't be it. So it's a silver lining for me. So I'll present some work that's joint with
Ziad, I
Sendal.
have a rash I need you to take a look at. I can show it to you on video.
No, the resolution just isn't going to be.
I actually
luckily,
think
we're
the
both in
virtual
Berkeley.
medical appointments work well.
This work is joint with Sendal, and the starting point is actually also a clinical starting point, which is that very common dilemma that doctors face, whether it's in the ER or in clinic, is when people come in with a range of symptoms that could be consistent with a heart attack. It's a surprisingly broad range of symptoms from chest pain to trouble breathing to nausea. And when you're working in the ER or in the clinic, you can do a couple of easy tests on the patient right in front of you. But the problem with these easy tests is that they're often inconclusive. So they can be reassuring, but the person can still be having a heart attack. And that's what has given rise to a whole range of elaborate and expensive and invasive tests to definitively answer the question of whether or not patients are having a heart attack. And so this is kind of putting someone on a treadmill, it's threading a catheter up into their coronary arteries. I'm just gonna group all those things together and call them testing. We can break them out if we need to, but since they all fulfill the same kind of cognitive function, which is getting a definitive answer, we're just gonna consider them all together. So it's a hard decision subjectively when you're working in the ER, but it's also hard when you there's corroborating evidence from health economics that this is a hard decision, because when you look at the yield of that decision, how often that test turns into a concrete benefit for the patient by yielding information on a heart attack and generating life-saving treatments potentially, the vast majority of the time, those tests come back negative. The patient gets no benefit, nothing changes in that patient's care or their health. And so we have an explanation for this. So, moral hazard, essentially doctors are paid by volume. And so it's unsurprising that doctors want to maximize the volume. But what we're more interested in is the fact that even, let's set aside all the incentives, this is actually an incredibly complex inference problem. And so what we're interested in is whether or not doctors make mistakes and in characterizing the nature of those potential mistakes. So the way, our starting point for thinking about this, and I think the reason that machine learning becomes a really useful tool is that testing is a prediction problem. Here's kind of like how we're thinking about it, at least. So the benefit of the test can only be known ex post. So the benefit of the test actually depends on its result. So if you think about, just writing a very simple way to formulate the causal effect of a test, the difference between the state of health in the world where the person gets the test and the state of health where the person doesn't, that's the product of two things. It's whether or not the test is positive, and then the person's treatment effect from all of the treatments that are unlocked by that test. And so, testing generically, we're going to be comparing the state of the world with or without. Testing for heart attack, we can actually sign it and say that a positive test is a useful test. And we're going to, for the moment, abstract from false positives, false negatives, et cetera. A positive test is a useful test because it unlocks the ability to deliver potentially life-saving treatments. So if I diagnose a heart attack in the ER, that person is a candidate for a lot of aggressive therapy that can add enormous numbers of life years onto that person's life expectancy. That's good. By contrast, if that test is negative, it's a wasted test. In other words, I've incurred all of the costs, and those are, of course, financial, but also a lot of these tests have risks in terms of radiation exposure, surgical complications, et cetera. All of that without getting any benefit from that test. And so one way to think about the job that the doctor is doing in allocating tests is she, before getting the test, is going to be predicting the likelihood that that test will be positive. If that likelihood is above some threshold that's dictated by the cost effectiveness of all of the downstream things, then you go ahead and do the test. And if it's insufficiently likely to be positive, then you don't do the test. There's a mechanical reason that you can't deliver the treatment without doing the test. In other words, if the main treatment here is putting a stent in the coronary arteries to open up that coronary artery. To do that, you actually need to first test so that you can see where that blockage is. If there's a blockage present, you put in the stent. So we can kind of come back to some of these, as we call them, institutional details in the question and answer. So this is the problem. This is one way to think about, at least, the problem that the doctor is trying to solve is predicting who is a good candidate for testing based on their ex-ante likelihood of having a positive test. The test confirms that. So what we do is we form explicit predictions on the results of those tests, and we compare those algorithmic predictions to the doctor's implicit predictions that are revealed by their decision of whether or not to test someone. So the doctors see the threshold of risk, they draw the line, and they test above that threshold in a kind of idealized model. And concretely, what we do is we look at people who have gotten the test, and we see, for those people who are tested, who goes on to get treated. So this is assuming that the test comes back positive, and then the treatment is delivered. And so you might wonder, why don't we just predict the test positive, like the presence of heart attack? That's very poorly measured in our data. And in fact, the treatment is really what we care about. The treatment is the benefit of testing. Testing is just information. The benefit of that information is leading to treatments. And so what we actually have the algorithm predict is, among those people who get tested, who goes on to get the treatment that indicates that that test was positive and that they would benefit from the treatment. I'm just going to put up these caveats at the bottom that treatment decision might build in overuse, which you might be worried about, and that in this framework, we're essentially zeroing out any psychological benefit of knowing that you don't have a heart attack. Those are things we can come back to in the discussion. I'm going to abstract from most of the details of actually fitting the machine learning predictor. Here is at a high level how we do it is, imagine a patient's kind of timeline before and after they come into the emergency department at time 0. Over the 3 years before that visit, we're going to aggregate all of the data that we can from the hospital records. So this is diagnoses, but also laboratory studies, vital signs, all results of prior testing, et cetera. We're going to come up with a list of about 16,000 features. Features is what machine learning people call variables, just so you guys know. We're going to then use those features to predict our outcome, which is, among those people who get tested, who goes on to get treated. And we're going to look in the 10 days after that emergency department visit. That's the guideline recommended period where, if you want to test someone for heart attack, you should do it. Most of the action, 80% of the action, is in the first 48 hours. So these are tests that are happening in or right after someone's ER visit. We put all that together in a sample of, it's a sort of census of a few years of data from one big hospital ER. And what we do is we split the sample. So we train the algorithm on a 2/3 sample of patients, not visits, because patients have multiple visits. So we want to keep those separate. And then all of the results that I'll show you are from this independent holdout sample of patients that the algorithm has never seen. So here's one way to just get a starting point on how well doctors are doing with this decision. If you look at all of these tests that doctors are currently recommending, and you look at their outcome, the average yield is 12.5%. So conditional on getting the test, meaning the doctor is worried enough about heart attack that they send you to get these tests, you have a 12.5% chance of actually getting the treatment that indicates that that test was positive and that you got the health benefit from the test. So what I'll show you is a graph of, on the x-axis, we've just binned people into deciles according to their predicted risk, so low to high risk. And on the y-axis is that treatment rate, the yield rate. And as you can see, this curve is upsloping, which I think when we first got this set of results, we found somewhat miraculous, because remember, these are people, all of these people doctors are worried about enough to test them. And using data available to the doctor at the time that she makes that decision, we can actually ex ante predict the result of that test in terms of the the return, the treatment likelihood. So that's already kind of cool. The average line is down there at 12.5%. The lowest decile has a treatment rate of under 2%. The top decile is over 50% likelihood of getting the treatment, so it's a fairly big range. You can think about that, you just translate this into cost effectiveness units using the normal set of numbers that happen in this literature. This lowest decile is, by any standard, not at all cost effective. By contrast, as you can imagine, that top decile at a 50% likelihood of having a heart attack if you're tested, that is very cost effective. And so seeing that range, you can see, okay, well, it seems likely that we might want to cut these low value tests on the left hand, where there's very low cost effectiveness. These other tests on the high end, though, those seem like a really good idea. And so you might wonder another thing. So all of this is the tested people. What about the untested people who have this high level of risk, like in the top decile? The algorithm sees them. We can generate those predictions for untested people, even though they haven't been tested. What fraction of those people actually are getting tested? And in fact, 57% of people that the algorithm thinks of as very high risk are not tested. And so that might make you think about undertesting. But undertesting it's kind of a different beast. And so this is where we have to shift into kind of a different mode. So we've been in machine learning mode, training and validation. This is all, I think, very clean. Now we have to kind of shift into what I think of as like detective mode and try to understand what is actually going on here. So one very obvious possibility, obvious I think to you guys, but I think not at all obvious in the computer science literature, is that doctors might have very good reasons for not testing. So we've fit our predictions in people who got the test. Now we're generating predictions for people who have been selected into not getting the test. And what's worse is that we have no way of evaluating the validity of those predictions because they haven't gotten the test. So doctors in this setting have a ton of private information. So we have all of the data available to the doctor up until the patient comes to the triage desk of the ER, but then there's a ton of stuff we don't see. So we don't see the doctor's physical exam, the patient's symptoms, apart from what she says to the triage nurse. There's a lot of private information that could very reasonably be used to do this triage into testing or not testing. And so we see someone who looks like they're very high risk, but because the doctor has used all of this stuff to make the determination not to test them, the yield for that person is almost certainly going to be lower than we think from the algorithmic perspective. And the reason I'm flagging this, even though it feels like I don't need to convince you guys that there's selection into testing, but I think this is a really underappreciated challenge of doing any work on undertesting, because by definition, we don't see the outcome of the test and we can't judge the quality of the predictions. And so that's why I think we have to instead turn to some like medical detective work. So it turns out that the consequences of untreated heart attack are pretty well mapped out in the medical literature. And here, using electronic health record data, we have this added benefit of seeing subsequent testing, like laboratory tests that might be consistent with undiagnosed or untreated heart attack. And so now what I'm showing you is untested people who have also been binned into these 10 deciles of risk. And these lines are the value of a laboratory study called troponin, which measures damage to heart muscle. So it's a very commonly done test. So we're looking in the 30-day window after this person was not tested in the ER. And we're just looking to see if another doctor at some point tested this person for a heart attack with this laboratory test. If negative, it doesn't mean they're not having a heart attack, but if positive, it means that there's damaged heart muscle floating around in the bloodstream. This is any positivity. So this can have a number of different causes, but now we're thresholding at higher and higher levels of that test, meaning more and more heart cells have been damaged. And so by the time we get to these lower lines, which basically only happen in the very highest risk people, these are pretty large heart attacks demonstrated by a biomarker. So I think that hopefully reassures you that at least in these high-risk people, there's something going on that they're high risk. But there is another problem, which is that maybe doctors are just choosing not to test these people, not because they don't know they're at high risk, but because they've already figured out that not only are they at high risk, but they're also for some reason not going to benefit from the treatments that the test would unlock. So remember, the way we wrote down the expected benefit of testing is the product of these two things, which means that there's this annoying covariance term. And so if there are people who have a high likelihood of testing positive, but a low benefit from treatment, then we're in trouble, because it means that the expected benefit of testing is no longer just a function of the likelihood of testing positive. It could also be that this negative covariance is working against us. And you could easily imagine that, for example, in elderly people who might have heart disease, but might be too frail to take all of the treatments that would benefit someone else. And so we do see some support for this. So this is the testing rate. The yellow line is the testing rate as a function of age. And so sorry, you can't, the numbers are very small, but you can see testing rate goes up with age until about 79, and then it starts going way down. And so this might make you very worried that doctors are indeed seeing these people saying, yeah, they're high risk. We know risk of heart disease goes up with age, but I'm not going to test them because they're not going to benefit from the treatment. Now, here's this other line. So this other line might reassure you, because instead what doctors are doing is saying, I know you're having a heart attack. So we've grouped together all of the diagnosis codes from that ER visit that are consistent with the doctor saying, I know not only you're at high risk, I know you're actually likely having a heart attack, but I'm not going to do the definitive test. And that is going way up with age. There's a clear billing incentive to record this diagnosis if you think it's going on, because you get paid more the more severe the case is. And so this seems to be going up with age at the same time the testing rate is going down. Now, if you look at the people who actually in that 30-day period, the untested people who go on to have a heart attack, you can actually look at their diagnosis codes too. And what you find is that doctors basically are saying, I don't know what's going on. So the discharge diagnosis, what the doctor has concluded at the end of the visit, is chest pain, I don't know why, short of breath, I don't know why, or pneumonia or arrhythmia, or these things that are kind of orbiting around, but there's no clear indication that the doctors are knowing that this person is at risk or having a heart attack, but still deciding not to test them. So just to summarize so far, not controversial that doctors overtest. I think one useful contribution that we're making here is that because we're doing this with hospital data that are available in real time, this really sets the stage for us to make some real contributions by building decision aids. And we're actually trying to work with some hospitals to implement this in a randomized trial now. I think that this potential evidence of undertesting fits with some things that you might have seen in the literature. Jason and Layla have this wonderful paper that I think was the first real evidence of this. Amitabh and Doug Steger have a paper that similarly shows that hospitals might be overtesting and undertesting. I think our contribution here is to really tackle that empirical challenge of selection into the observation of outcomes by doing this detective work and generating outcomes for the untested people where we don't have any feedback empirically. But stepping back, I think that what this also exposes is that we don't have great models of why doctors would undertest. Moral hazard doesn't explain why doctors are not testing these very high-risk people. And so what is the behavioral model here? One way that we've tried to get some insight into this is by using algorithms to model the physician alongside our models of risk. So the specific thing that we're doing here is we're taking this machine learning infrastructure and having it and basically hamstringing the machine learning predictor and saying, we know you have a very complex function. I want you to progressively simplify it. So one way to simplify it is by constraining the number of variables it can use. So if you look at the predictive accuracy of our machine learning infrastructure for predicting true risk, you see that as you increase the number of variables, that goes up until you reach about 120 variables, and then it starts to go down as you start overfitting. So this is a kind of standard finding in machine learning. Now, what we do next is we take those progressively simplified models of risk and we use it to predict not risk, but the doctor's decision. And here what we find is that the best predictor of the doctor's decision is not the full model, like the 120 variable model. It's a simplified model of true risk that only has 14 variables. So when we look at those 14 variables, the weights are roughly correct. So if we look at the correlation of a given variable with the physician's test decision, that also seems to map onto this correlation with the outcome with an R-squared of 0.4. And I'll just show you.
Yeah, Ziad, I missed the time. I should have said that you have a few minutes, but that's it.
Okay, I'll wrap up. Why don't I just skip ahead and just say that what that might suggest is that physicians are using a simplified but accurate model of risk that might look like a kind of bounded rational model. There's also another view, which is that physicians are making mistakes. So the last thing I'll leave you with is this idea, which is that imagine this patient with chest pain. A patient has a probability of having a heart attack P, probability of other serious stuff Q, and probability of like nothing or something trivial, the sum of that subtracted from 1. This patient's differential diagnosis is just heart attack. This is the only serious thing this patient could be having. A patient who's short of breath, on the other hand, that could be heart attack, but it could be a lot of other serious stuff. And so that person has the same risk of heart attack or greater, but also a greater risk of other things. So under a rational model, you might predict that these two patients are tested at the same rate. What we see instead is that patients with shortness of breath are actually tested less. Their yield is about the same, but they have a much higher rate of adverse outcomes. And so I think this suggests that physicians are being distracted by these other things, or that they're using stereotypes, that chest pain is very representative of heart attack in a way that shortness of breath is not. So why don't I just wrap up and tell you, we can come back to this later. Yeah, well, I'll stop there. Thanks, Andrew. Sorry for going a little over.
Thank you, Ziad. No, my problem. All right. So now we're going to go to Vikram, but we're going to go to Vikram in an unusual way because Vikram has given us a recording that we will play. And here it comes.
Hello, my name is Vikram Krishnamurthy. I'm a professor of electrical engineering at Cornell. This work is joint with my former PhD student, William Hoyles, and my current PhD student, Kunal Patnaik. The title of the talk is Rationalizing YouTube Commenting Behavior. Before going into the details, I want to say a few things about YouTube. So, as many of you know, today YouTube has more than 1 billion users, and amazingly, every minute more than 300 hours of content is uploaded to YouTube. What we're really interested in is how to model and predict user engagement in YouTube. That is an extremely important problem, as I will discuss below. So what does user engagement mean? In simple terms, how do the thumbnail, title, and description of a YouTube video affect its popularity? A related question is, how does the interaction of YouTube channels with users affect the popularity of a YouTube video? You see, YouTube is quite unique as a social network. It has interactions of users through video and commenting content. This is unlike Twitter or Facebook, where typically users interact with other users directly through messages. In YouTube, we have this additional video content, which can result in significant differences. An important question you may ask is, why do we care about user engagement? Well, there are several reasons. The original reason why I got into this area was because there are 5G wireless communication providers who, in the latest 5G protocols, want to figure out what multimedia videos are going to become popular. Because if they can predict what videos become popular, then they can adaptively cache or store those videos at a base station close to a cell phone so that the download times are very short. Also, people designing recommender systems want to know which videos become popular so that they can improve the performance of a recommender system. Another reason why I got interested in this area was because of content producers. So for example, in Vancouver, in Canada, there is a company called Broadband TV, and their aim is to suggest keywords, titles, and thumbnails for YouTube videos to maximize how many people actually watch a video. Keep in mind that YouTube is an economic system. For every 1,000 views, the content provider gets between $3 and $5. Now, the main result of this talk is highly focused on one aspect of user engagement. Actually, in previous work, we've looked at several other aspects of YouTube engagement, but in this talk, we want to focus on one aspect, and that is how to relate view count to commenting behavior. And we're going to do this by analyzing a massive YouTube data set. Now, and our main result is the problem tractable, that we will use a simple idea like machine review preferences together with classical economics type tools, the hypothesis that users are utility maximizers. So on now to the gives extremely accurate results for understanding how to relate view count to commenting behavior, consistent with Bayesian utility maximization. So getting to the model of a Bayesian utility maximizer, and with our YouTube application in mind, we start with defining the state X. This is the state of nature, so to speak, of a group of videos. We will tell you what we mean by a group of videos later, and these groups are constructed by using machine learning tools. So for a group of videos, we define the state X as either a low view count or a high view count. And X has some prior pi0, which we can estimate empirically by counting the view count of videos within a class after 1 day after the video has been uploaded to YouTube. Now, there are several subtleties in this definition, which we will discuss after this talk as to why 1 day is a reasonable time period to wait for the prior, but let's just assume that for the moment. The next ingredient is the observation that users who comment have noisy measurements of the state X. So users, in other words, observe the view count in noise. In more sophisticated terms, users get visual cues about the view count of a YouTube video as explained in this snapshot here. So this is a typical picture of what you encounter when you go onto YouTube. And you see the view count. Now, the visual cues are things like the thumbnail and video description. So when you go onto YouTube, you see the thumbnail, you see the video description, and that gives you a noisy observation. You have then the conditional probability Y as the probability of this observation given your state X, where this conditional probability is the attention function of the viewer, and we will link this to a rational inattention term shortly. Now, the observation causally causes the YouTube viewer to take an action, namely lodge a comment. And that is clear from the construction of YouTube. When you first look at a YouTube video page, what you see is the view count, you see the meta descriptors such as visual cues of thumbnail and video description, and after that, you actually click on the video and then see comments and add your comment. So it's a completely reasonable assumption to make that you make your action based on your visual cues of observation. Why? The action here is where we're going to quantize it, and for this we use some sophisticated natural language processing tools to have each comment to either be high or low in terms of the number of comments on a video. And also we look at the sentiment of the comments. Are they positive, negative, or neutral? So in total, there are 6 actions: high, comma, low, Cartesian product of positive, negative, or neutral. Then we come on to the next important ingredient in our Bayesian utility maximization model, that of the utility function. In this case, the utility function is the commenter's reputation. Let's call that U of X comma A, where X, again, remember, is the view count, and A was the action taken by the particular commenter. We can now formulate the problem of optimal commenting behavior as the following optimization problem, where we denote C of alpha pi 0. Remember, pi 0 is the prior, alpha is your attention strategy, so to speak, as a rational inattention cost. Then optimal commenting behavior is equivalent to optimizing the attention strategy and the comment to maximize the utility function minus the rational inattention cost. The rational inattention cost being how much attention does a user spend in looking at the visual cues in order to lodge a comment. So this is a model for how optimal commenting behavior might take place in a YouTube social network. Now, the analyst, that is us, who has a data set of YouTube, would like to check if this type of Bayesian utility maximization model has any relevance to a YouTube data set. And as we will discuss, the surprising result is we have good fit of this model together with several robustness metrics, which tell us that optimal commenting behavior is an extremely accurate way of viewing how users comment on specific groups of videos. Now, I mentioned the term groups of videos, and let me just abstractly mention it here, and we will justify that very soon in terms of how we group the videos based on content and how we group the videos based on user-centric properties. So this is the analyst's aim. And so given pi 0, that is the empirical prior, and we told you that pi 0 was computed by looking at the view counts on the first day after a video was posted. And given the probability mass function of the actions given the state, this is like, if you like, the comment strategy of the different users given a state. And M here denotes specific classes of videos. And so we have here M different classes, and we call these classes agents. The aim of the analyst is to say, given this data, is it consistent with optimizing commenting behavior? So pictorially, what we're saying here is we look at the empirical distribution of the prior, we count the different actions taken by the commenters for various states X, which is low view count and high view count, because we know X as time progresses as the analyst, so we know the true view count. So then it is a fairly well-known solution today. For example, the paper by Andrew Caplin and Dean in 2015 show that if based on pi 0, PM, and U, then we can reconstruct utility functions, and we can also say if the behavior is consistent with utility maximization as the solution of a convex feasibility problem. So thus far, I've said something fairly abstract, essentially the idea that the commenting behavior in YouTube by individuals is consistent with Bayesian utility maximization. Well, in the rest of the talk, we're actually going to justify this in some detail. So we have had access to certain inequalities hold at a massive data set of YouTube corresponding to 140,000 videos over 25,000 channels. And we can justify many of these results based on that massive data set. Now, the first task with this data set is this issue of grouping videos into specific classes. And that can be done in two possible ways to achieve some form of dimensionality reduction. One could be a user-centric approach, where, as my student Kunal will point out on the next slide, one can use ideas in deep clustering to map thumbnails and descriptions into tractable quantities so as to group videos which are similar. Another way of grouping videos is content-centric, basically the video category. Videos which deal with education form one category, for example, videos which deal with political situations form another category. So one can think of two broad categories of classifying YouTube videos. Remember, each category here can be viewed as an agent, and for each agent we have a prior and we have an action selection policy, and our aim is to show that that prior and action selection policy is consistent with Bayesian utility maximization with a rational inattention cost, where we will say further things about the rational inattention cost in both terms of Shannon entropy and more general Renai entropies, as we will discuss in the next slide. So before jumping on to the next slide, I just want to state the main result, as we will justify, that YouTube commenting behavior is consistent with utility maximization, and therefore the estimated utility function U can be used to predict commenting behavior of users, something like 83% or higher in many cases. So that means if you give me a video, I can, by knowing which class the video belongs to, I can now use this utility function to predict what will be the commenting behavior in terms of the number of comments and the sentiment with extremely high accuracy. Okay, so I'm now going to go on to the next slide, which my student Kunal is going to present, which deals with the general ideas of how auto-encoding is done in order to form various groups of YouTube videos, and a detailed analysis of the data set itself.
Okay, so now it's probably time for Kunal to present his part very briefly.
Kunal, are you there? Able to speak? Otherwise, Vikram, I mean, we should keep it going.
Right, I can't hear you, Kunal. Can you hear me?
I'm sorry, yeah, I think I kept the mute button on. I'll just
Okay, now I can hear you. Go ahead.
Okay, and share screen again. Thanks.
Yeah, I'm sorry. Yeah. So thanks so much. I'm Kunal. I'm a third-year PhD student at Cornell University. So I'll jump right in. So we partition the YouTube dataset by grouping together videos with similar thumbnail and description, which is what the viewer first sees before interacting with the video. Now to do this, we use a deep learning architecture comprising two components. One is the autoencoder and the other is the clustering layer. What the autoencoder basically does is it uses text processing tools like word2vec and image processing tools like convolutional neural nets to map the raw image and text data to a vector, a 200-dimensional vector. The clustering layer then maps this 200-dimensional vector to a 2-dimensional Euclidean space and also performs a great job of partitioning the dataset into 4 non-overlapping segments. Now, for the sake of analysis, we divide each group into 2 further subgroups of gaming and non-gaming videos and carry out a utility maximization feasibility test on each of these colored regions, taking the non-gaming and gaming videos as 2 agents. Now, our test uses 3 types of cost structures for fitting this data set to a utility maximization model. We first use the general cost structure, which basically puts no constraints on the rational intention cost the agent has to take on. We then use specialized cost structures as the Renyi and Shannon mutual information cost. The Shannon mutual information cost is a typical choice to use given the paper by Christopher Sims in 2003. Renyi cost is basically a generalization of Shannon cost, and it will be shown that it's basically parameterized by beta, and the Shannon cost is a limiting case of Renyi cost as the parameter beta tends to 1. Now, our test output showed that all 8 clusters passed the convex feasibility test for the general cost case. However, for the specialized costs, only 2 clusters go through. We also adopt a second approach for partitioning the data set based on the video topic, like gaming, politics, education, etc. And this gives us like 18 clusters in total, which is basically a higher granularity compared to just 8 clusters in the previous deep clustering approach. Now, the output, again, we see a good fraction going through. We see like 10 categories satisfying the general cost and just 2 going through for the Renyi one. Now, the estimated utilities do yield valuable insights. And what we'll be focusing on right now is that the categories that don't go through fail by just a small margin. And this leads us to carry out a robustness analysis, which basically deals with how close are these guys to.
Kunal, I don't mean to be pressing, but you're going to have to get fast on the last slide or 2. Thanks.
Understood. Yeah, I will be finishing it in under a minute. Yeah, so this basically brings to the concept of robustness. How well do the model fit the data set? So we saw that. So our major finding was that the clusters that fail do so by a really small margin compared to the clusters that pass and how much we need to push them so that they fail. The ratio we found to be pretty large, which is 6, which basically says that you need to perturb the data set by a much larger value for them to fail rather than getting those guys that fail to actually pass. And this concludes that our utility maximization model is indeed a solid fit to the general cost structure case. Finally, for the parameterized costs, we saw that, again, a small perturbation is enough even for the more restrictive Shannon and Renyi mutual information cost structures. On the left-hand side figure, we show the minimum perturbation needed for the 10 clusters that actually go through to pass for the Shannon case. On the right, we have as a function of beta, what's the average perturbation I need to give to the data set so that the Renyi structure goes through. And we can see that the data set fits better for values of beta like closer to 1. And all in all, we can conclude that the typical YouTube commenter is rationally inattentive for a wide variety of rational intention costs. Now, for lack of time, I'll just put on the last slide, which discusses the extensions and limitations, and we'll be happy to take it on in the discussion session. Yeah. So that's me. Thank you.
Thank you very much. Now let me organize my own discussion. Can you see my screen?
Yes.
Yes, Andrew.
All right, so I'm going to discuss these papers, which are, I think, part of probably one of the most important moves in applied economics, which involves, as far as I'm concerned, the general subject, and this is much of what rational inattention theory and alike is about. The general subject is measuring and modeling mistakes. And we're going to see how machine learning, economic analysis, and policy come together in intriguing ways. And I'm inspired by the two papers, but I want to step back and try to give you first a bit of a bigger picture, certainly for what I see is going on. All right, this is the game, so as I see it. We are actually, if you're kind of a big fan of the history of economics and what we do, then you'll know that the information revolution has been around for a long time. And I actually think we're not at the beginning of the end of the information revolution, but the end of the beginning, because we had previously not taken the empirics of identifying what people know all that seriously, and why they know what they know and why they don't know what they don't know. But that seems to be rather critical, and it's assumed in many models. What you can attend to, what you can understand and comprehend, what you retain is key. We've seen in these talks to education, income, saving lives, YouTube, tax incidents, asset pricing, you name any sphere of human behavior. I can't think what it's not important for. And I believe it's on the same long run level of importance as standard production and utility theory. All right. Why measuring, modeling, and minimizing mistakes? Well, look, in applied microeconomics, there are 100 case studies of mistakes. People overpay in rather obvious ways for insurance. There are two dominated products. They pick the dominated one. One dominated, one undominated. Now, traditionally, it had been explained when I saw people doing things, I tended to explain it, lots of strange choices with random utility, that they liked the alternatives sometimes. But that's very hard with dominated options. But when it's not dominated options, that explanation always seems to be feasible. So the random utility model is allowed to explain behavior when mistakes are everywhere. It's just they don't come with labels, except in the case where you don't get 100% on the exams. I think that's true, and that would be a mistake. Where you overpay, that's a mistake, but mostly it's just a decision. It's hard to tell which decisions are mistakes. They don't come with labels. So Bloch and Marshak long ago said, here's a major problem. We don't know how to separately identify utility beliefs and beliefs. And where does policy come in? Well, maybe you have attention policies, such as letting a machine taking over a bit of a decision, as would obviously seem to be optimal in the case of heart attacks, given the mess ups. So that's one of the most important outcomes of MO, Nathan Obermeyer. So why such data-rich approaches? Why are they coming in? Why machine learning? Then I'm going to go to the ideal 5-step research process, and relate back to the papers we've just seen. All right, I think there is a fairly clear general data set that is being used, but maybe it's not generally being labeled as such. The abstract data that people are increasingly gathering is state-dependent stochastic choice data. It's not just stochastic choice data. If somebody's sorting beans and they're supposed to sort them into large and small, marks 20% as large, that's not all that informative about what they understood. It's much better if we could observe the actual size of the beans. Ideally, an ideal observer can see the mistakes they're making. Psychometricians realized about 200 years ago that this was a good data set, and economics has been following about 190 years late. But it's actually the data set that's increasingly in use. In the M&O paper, the analyst knows various health outcomes and whether, and the doctors perhaps not. In HKP, the analyst knows how viral a video is, which is apparently very important. The commenters perhaps not. In tax salience, the analyst knows the tax rate, buyers perhaps not. In quality control and production, the firm might know the quality, and obviously the person who's producing a defective item didn't believe they were. Now, this data is absolutely spectacularly rich. You've got in the medical case file, the state. What's the state? It's a huge thing. Everything that could have happened in prior diagnoses, the actual diagnosis this time, subsequent health outcomes. In YouTube, thumbnails, comments, labels, ex post popularity. You're not going to get anywhere analyzing this data unless you know how to handle data that's way beyond what we had ever developed before in economics. And it's going to be machine learning that's going to be required in that step. What can you do when you've got the data? You can test theories, you can recover costs, and Bayesian RI. I think what you saw is that in HKP is that Bayesian rational inattention models are now usable, and beyond Bayesian is the next frontier, and that's a little bit what MO are talking about. We're going to go to something that isn't purely Bayesian. The ideal research process as I see it. Step 1, define model objects. These are actions and prizes. It's not very complicated. What can you do? What can you earn as a result of doing? This is for the decision maker. We're trying to explain what they do. There's some underlying state that if they knew it, they'd find out the prize they were going to get, and they would therefore know their utility. We need to know these utilities to motivate their learning, otherwise why bother? They have to have prior beliefs over states. They then extract the information they can, end up with signals and posterior beliefs, and they must have costs of learning to motivate the information constraints. I'd like to say that I don't know of a smaller set of model objects that is interesting to work with. I do know of much larger ones that are interesting to work with. You then gather the state-dependent stochastic choice data related to all of these model objects. That's easier said than done, but there are opportunities everywhere. We've seen some exploited just in these 2 talks. Next step, map model to data. The standard is a Bayesian mapping where you extract the posteriors associated with the posterior distribution over states associated with each of the actions you see picked. That is the minimum that you could say, well, they had to infer at least that much. And the mappings for other theories, which are non-Bayesian, have not yet been specified. They're very interesting to do that, but it hasn't happened. You can then test theories, and machine learning is a very interesting thing to do here. It helps contrast what could have been known with what apparently was. So there was some ideal amount of learning that could have been done. The machine might be able to extract that. But apparently that's not necessarily what was known by the decision maker. If we find that a Bayesian model can pass, then we can infer the utilities and the costs from the data, and it might be very different than what the ideal machine would have done. If the Bayesian doesn't pass, and if there's a clear fail, no improving action switches, fails is the only direct test that you kind of failed the Bayesian thing, there was something much better you could have done, it will suggest a non-Bayesian alternative. And it's very hard to model this because how do you invest in learning based on an illusory level of learning? What do you believe is the cost of becoming deludedly informed? It's an interesting, very interesting abstract question. After that, you do standard utility policy analysis, changing utility, present the information differently, offer advice, do it, replace with a human with a machine, or blend. Now, in that five-step process, I'm now going to step back and say of those 5 steps, what do the 2 papers do? Muller, Nathan, and Obermeyer, MO, they major on step 2, which is getting the extremely rich data. On step 5, which is I'd like to do some policy analysis and improve the decision making. And they minor in 4, which is what's a theory for the gap I see between the decisions that should have been made and the decisions that were made. Now, their policy proposal, 5, is pretty clear. Get rid of the doctors. I mean, replace them with the machine, which seems to be doing much better than them. If you can't do that for various reasons, at least try and nudge the doctors into being less awful. And it looks like the mistakes have patterns suggestive of non-Bayesian inference. But I had 3 questions reading the paper. The model of the decision maker is to test if above threshold risk. And I didn't see that as accurate in positive terms. I don't know that that's the decision. I think there are other incentives involved. Is that what the analyst would like it to be? It seems imposed as an ideal, but not a real motivation. It's also a little too crude as it was for the policymaker who could work on years additional life. We could think of many things that are going on. Not that this explains behavior, but I just don't know what the utility function is. And then it's also, I believe, unrealistic for the decision maker if they're worried about, e.g., lawsuits, test wealthy, or if they're prejudiced. There are certain people they just wouldn't mind if they died. I don't know that's what's going on. I don't know that. Also, the non-Bayesian finding depends on patterns based on the neglect of information that should have been taken into account in the diagnosis. But should have been doesn't mean it was internalized. And certainly, if other legitimate goals guide behavior or this particular thing leaves an unanswered question. If I don't understand why the mistakes were made from the subjective viewpoint of the decision maker, it's hard to redesign the evidentiary base so that the decision will improve. I don't know what they'll do with a redesign. All right, HKM. They work on steps 1 through 4. They have a novel model structure, which is the utility of the pioneer viewers on YouTube. I want to comment that I found this totally fascinating. I have no idea what motivates people on YouTube. I'm really bad at understanding this since I don't typically watch very much and I wouldn't comment if my life depended on it. Apparently the idea is that you're trying to achieve influencer status. You kind of watch the video early. You'd like to say, look, there's no point commenting on a video that's not popular. That's not going to get me anything. What I want to do is comment on a popular video. It'll go viral. My comment will be seen by many. If I make the same comment as many others do, for example, then apparently I'll be seen as a leader and that has status for me. So their data is super rich and include ex post knowledge of popularity, which is the state that matters. They do test the standard Bayesian RI theory, and it passes and find it to be useful for prediction. And I want to raise two issues there. The model is really of an extremely subtle situation. I think it's subtle beyond what they acknowledge. It's in a way, a sophisticated variant of Rosie Nagel's beauty contest. Like, well, what's going on here? I am trying to predict whether other people will like a video I see based on limited evidence for this. So that model is just fascinating, and it isn't quite there. The other thing is an unanswered question on YouTube policy. All right, how would changing easily accessible information in the thumbnail make it, would it be worthwhile to do this? They have a cost function for learning from the thumbnail. Could you teach YouTube how to design a thumbnail that made it more predictable and might therefore get better information out on virality and the comments? Everybody apparently would be Pareto superior. So that's my comments. Thank you. I think I should allow both Ziad and Vikram to respond, and then we can take questions from all.
Thanks, Andrew. I just wanted to make one point on the, I think in an idealized world, if all information were observable, it does seem fairly clear that you just want to replace the human. And so you can imagine that kind of world on some level, like when you have sensors on everyone 100% of the time and you have machinery to ingest all of this like today unobservable stuff. I think the reason I find that scenario hard to believe is because there's like an infinite amount of potential information. So there's always more questions the human can ask and elicit and things like that. And so one thing to remember is that in all of our, like, we're looking at the people who got tested and we see the yield in the tested. That's where we're on the firmest ground. And so there, when we're looking at those people, you know, there could be unobservables that physicians are using to test, but those all net out in some bin of predicted risk. So when the yield is low, we're pretty confident that the yield is low. In the untested people though, you know, we've got a kind of natural experiment set up where the testing rate moves up and down exogenously. And so we can see what happens when doctors test more or less, but only in that range of testing. There's this whole bottom of the iceberg that we never get to observe. And those are the ones that I would be most worried about in this world where you're trying to generalize from where the machine has data to where it doesn't. Now, in a world where everyone is tested and you see everyone, then I'm less worried about that. And then we can have a fair comparison between the human and the machine, but in period 0. But then when the machine starts running and then period 1, you have like change. So I actually don't know if I would even generically agree with the replacement, just because of the complexity of the task and the amount of unobservables and potential unobservables that you could have but don't.
Thank you. Vikram, would you?
Sure. Can you hear me?
Yeah, and Kunal also. You both.
So let me first start with a few comments, and thank you for your comments. This is actually, YouTube is a really kind of economically interesting thing because, as I mentioned, there are several companies today whose business model is to suggest to YouTube providers how to choose a thumbnail, how to choose a title and keywords so as to maximize how many people watch your video. Now, you can imagine this process going on in a dynamical way, whereas in this talk, we just described a very simple static situation that as you monitor the view count, you could adapt your keywords and title so as to improve the popularity of your video. Now, one of the companies which we dealt with, which is Broadband TV, which is actually the largest producer of YouTube content in the world today, it uses very basic machine learning ideas to figure out if something is popular, and also how to choose things like the title and keywords. So how does it choose the keywords? You provide it with sort of like keywords you would like. And what the company does is it finds the closest entry on Wikipedia and puts that as a keyword. Really simplistic, but they say it does a fantastic job. How do they pick the thumbnail? The thumbnail is an image summary of a video. They look for a high resolution human face, and they simply put that, and they believe it does a good job. So the point is that there is substantial motivation to come up with much more sophisticated ways of doing that, which can be more efficient. Now, on the flip side, as I mentioned, people get between $3 to $5 for every 1,000 views of a YouTube video, and there is a lot of clickbait, basically videos which come up with a ridiculous title so that people just click there. As long as they're about 20 to 30 seconds in a video, they get their basic money for each view. So the question there is, how do you kind of correlate between videos which are clickbait, or how do you detect videos which have clickbait compared to genuine videos? So this area is actually very, very important, not only to content providers, but also, as I mentioned, to telecommunications industries, because they're interested in providing to you on your cell phone content with very minimal delays, and that would entail storing popular content at the closest base station. Another point I just thought I'd mention, which I didn't mention in the talk, is we've done a lot of other analysis on the YouTube data set, apart from what we've mentioned here. And there are lots of interesting dynamics in that. We've seen, for example, suppose there is a person who posts content on YouTube periodically, say every Friday afternoon at 3 p.m. If that person misses that Friday and posts something on a Saturday, the view count goes up enormously because people believe that person has something interesting to say. So people can deliberately spoof all kinds of things to substantially increase their view count. And there's also this process of herding, right? Because if everybody picks titles and keywords which sound very fancy in a particular theme, eventually you lose resolution from all the other people who use exactly the same terms, and then your popularity goes down. So there are lots of interesting dynamics in YouTube, and these are things which are definitely worthy of further research and investigation.
Thank you very much. We should open to questions from others, and I've seen something in the chat to Ziad. Is that right, Ziad? There's some.
Yeah, Frank asked a great question, and
Good.
Jason also posted a comment.
Please bring that to us.
So Frank made the great point that human patients might be more interested in getting recommendations from human doctors. And there's actually some evidence from actually joke recommendations that people prefer jokes recommended to them by humans and think that they're going to be funnier. So I think that that aside, my sense is that—
Couldn't you have the human deliver the machine's verdict?
Yeah, and I think that's where a lot of people think medicine is heading. Like, you know, the doctor is the velvet glove, you know, on the machine.
They are doing that anyway, just a bad machine.
Just a bad machine, yeah. I think a good model is like, you know, airplanes, where I think people would be somewhat uncomfortable if they got on a plane and it was like, yep, it's just the human. No, we're doing this on original instruments. And so I think that's not a bad model. And I think it's also optimal given, you know, there are exceptions. There are instances that are way outside of the support of the data. That's why we have humans flying airplanes. There are lots of unobservables that the machine doesn't have access to. So I think that like the way we're thinking about, for example, our randomized trial intervention. So we're working to implement this in a real setting where essentially what we want to tell the human is the algorithm is going to give you a very good prior integrating all of the information from before the patient ever walks in and goes in front of you, that's where we want you to be anchored. And now you can kind of like, you can modify that. You can update however you want based on your unobservable information, but at least we've anchored you at the right prior.
Do people have other questions? We are going to,
If I may interject, I've seen that Jason Abaluk had a question to Vikram. Perhaps I can just read it, unless he would like to ask it himself.
Jason, go ahead. Go ahead, Jason, I see you.
I asked in the text, but basically my question was, for the purpose of just predicting what YouTube videos become popular, is it necessary to put all this structure on utility maximization? Could you just use some more unsupervised approach, and does this approach do better?
Excellent question. So previously, we have looked at several types of ways of trying to predict popularity. Notice in today's paper, what we discussed was the reverse problem. By looking at view count, how do you predict commenting behavior? With the idea that if you can actually do that, then maybe you can invert the process and saying, given commenting behavior, you can predict view count. So today's talk was highly structured. But for popularity prediction, you're absolutely right. There are lots of ways of doing that, again, depending on the type of YouTube class and so on. So there are time series analysis methods, for example. You can simplify the time series and say, you can look at, of course, things like deep learning methods. So you simply train a deep layered neural network to give some estimate of the popularity based on already training on lots of samples on YouTube. There are several other ways as well. And what we've found is that for popularity prediction, it's quite non-robust in many cases just to a black box model. The more information we can feed in, particularly dynamics, and that's something, again, I haven't touched in this talk, but the popularity count often evolves over time based on extraneous information of what other videos in a related channel are doing. So there is this interaction dynamics, which I haven't even spoken about in today's talk. And so there are other complex things which, if properly modeled, can do a substantially better job in predicting popularity of videos.
I want to comment that that it wasn't us who forced Vikram to be thinking this way. Vikram started thinking this way, and inverse reinforcement learning is an entire field that's motivated by the Lucas critique, even though they don't know it, which is they want to recover something that is more stable across situations, and they think the utility function and the cost function might be. So it's not that we taught them X and they just kind of idiotically used that thing. They actually find it helpful to have stable underlying structures. And they have the same instincts that we do, which is that utility and costs are likely to be more stable than decisions.
Right. But then the question, of course, is...
So you can imagine, for example, a robot trying to learn from a human. Now, the robot is trying to come up with a utility function which adequately explains what a human is doing. And that would be the classical inverse reinforcement learning.
Right. And then the question, Andrew, is stable with respect to what counterfactual? Like, if you, any structural model is stable with respect to some counterfactuals, not with respect to others. So if it's not a pure prediction problem, then we need to know that counterfactual that we're interested in.
Yes, absolutely.
I find it ironic that the machine learners are in favor of recovering utility, not the economy. Okay, understood.
Andrew, I had one other thought on your great point about, is the decision maker actually using a threshold, and what could be going on? With your permission, I'll just share one little slide, which is that, I think the typical model is really what you were saying, is that there's some distribution of risk. The doctors are supposed to be drawing a line at the gray line, but they're moving down in the distribution because they're worried about lawsuits, because of incentives, et cetera. So that's like the threshold too low model. And I think that, Jason and Leila's paper, among others, were starting to suggest that that might not be the right way to think about it. So if you think about people being misranked, as in the bottom distribution, you can move the line up or down, but then you're still going to be drawing arbitrary marginal patients. And that is in fact exactly what we find when we look at testing rate. So if we have like doctors can test more or less. So they test more or less, but they kind of like, do so across the whole risk distribution. And we see that in the national data as well. So high testing hospitals test everyone more, low testing hospitals test everyone less. And it's just kind of like the marginal patients are everyone.
Excellent. We've run over time. So let's take our 12:55 break at 1. Thank you so much. And we can actually regather on time at 1:30 after eating for slightly shorter time. Thanks.